If I were to ask you what the most important advancement humankind has ever made, what would you say? Many would make the case for fire. Our species was in an evolutionary rut until we harnessed its power. It gave us the warmth to survive harsh winters. Its light extended our day, its destructive powers gave us a weapon against predators, and it allowed us to cook our food, which allowed our brains to grow. Our discovery of fire transformed not only our technologies, but our culture and our way of life. But I would argue that we are currently living in a time of equal or even greater change. We are living in a time of incredible growth, one that has already started to transform the way we live our lives. The age of information. With 40% of the world's population currently connected to the internet, the human race is more intertwined than ever before. But what led to this amazing tool? What single invention gave rise to our smartphone-equipped generation? The transistor. The transistor is information itself. Even this video is just a series of ones and zeros beaming across the planet to be interpreted by the processors in your computers. Without the transistor, I wouldn't have access to the wealth of information online to do my research, I wouldn't be able to use my animation software to make these videos, and I certainly wouldn't be able to share it here for the world to see. The transistor is so simple, but it is the foundation of all our modern computers. To understand its impact, we need to understand the history and science behind it. Before the transistor existed, we used vacuum tubes, which are these bulky evacuated glass bulbs. The triode vacuum tube consisted of three parts: the cathode, grid, and anode. A current is passed through the cathode and it begins to heat up, causing it to release electrons. As gases have been removed from the tube, the electrons have very little resistance to their movement, and they are attracted to the positively charged anode. This completes the circuit, and a current flows. But we can manipulate this flow of electrons in many useful ways with the grid. For example, we can use it as a switch. If we place a light bulb here, it will only light up when there's a positive voltage across the grid. If we apply a negative voltage, the negative charge will repel electrons trying to pass through. This is the foundation of binary coding, which is the ones and zeros that gave birth to the age of information. Here 1 is a positive voltage and 0 is a negative. 1 turns the light on, 0 turns it off. The world's first general purpose electronic computer, the ENIAC, used 18,000 vacuum tubes to perform calculations. Designed by John Mauchly and J. Presper Eckert, it was completed in 1945. It was purpose-built to calculate trajectories for artillery during World War II. A calculation that would take a human a day to calculate took ENIAC 30 minutes. But this thing weighed 30 tons and took up an entire room. It was incredibly power hungry, as the vacuum tube cathodes needed to be heated to work, which also meant that the vacuum tubes burnt out regularly and needed to be replaced. All this to perform a function that your phone basically does with Angry Birds. Today, its computing power could be contained on a silicon chip no larger than a grain of sand, and that's thanks to the transistor. A modern phone has around 2 billion transistors, which perform the exact same job as the vacuum tube, but on the nanoscale. Let's look at how it works. Many of you will recognize the transistor as one of these, but this is a through-hole transistor that you can buy from hobby electronics stores for your DIY projects. The transistors in your CPU are microscopic and are manufactured with incredible precision with machines on thin wafers of silicon crystal that are sliced off silicon ingots like this. So what makes silicon so special that an entire section of the San Francisco Bay Area has been nicknamed after the material? Silicon is a semiconductor, which means its conducting properties can be tailored by introducing impurities to the crystal structure. Silicon has 4 electrons in its valence shell. This is the outermost orbit for electrons, and it determines many of the chemical properties of the atom. Atoms want 8 electrons in that shell, as this makes them very stable, so silicon readily forms covalent bonds with 4 neighbouring silicon atoms to gain those extra electrons. Now, if we introduce those impurities to this pure silicon crystal, we can change how it conducts a current. If we add phosphorus, which has 5 electrons in its valence shell, the extra electron is left free to roam the crystal structure. This extra electron makes the n-type negatively charged, which is where the name comes from. The p-type is positively charged because it is doped with boron, which has 3 electrons in its valence shell. This structure wants to gain its final electron, and will steal electrons from its neighbouring atoms. This creates a mobile positive charge, called a hole. The conductivity of the material has thus been increased, as we've increased the number of mobile charges. When we arrange n-type and p-type semiconductors like this, and attach terminals to each, we create the world's most prevalent transistor, the NPN transistor. The transistor works due to the interaction of those free electrons and holes at the n-type and p-type junction. Free electrons in the n-type will migrate over to fill those holes in the p-type. This creates a boundary layer called the depletion layer, which prevents more electrons passing through due to the negative charges repelling each other. But when a positive voltage is applied to the base, it negates the depletion layer and allows current to flow through, completing the circuit. As you can see, this is very similar to the function of the vacuum tube. So how exactly does this allow computers to perform all these complex functions that we see today? Let's look at a very basic example. Let's add 2 numbers together. First, we need to learn how numbers are represented in binary. That's the ones and zeros that are used to store data. This is the number 15, which is the largest number you can represent with 4 bits. The first bit represents 1, the next 2, then 4, and finally 8. Added up, that equals 15. This pattern continues, with each successive bit representing double the previous, so we can add an additional bit if we want to count up to 31. Let's add 5 and 6 together. To do this, we want a circuit that will hold a 1 in this position when either are 1, and carry the 1 forward when both are 1. As you can see, this will give us the number 11. The simplest circuit that can do this is a half adder, which contains 2 types of logic gates. These are devices that can modify the binary code. They are built using transistors. The first is the XOR logic gate, which gives a 1 only when one of the inputs is 1. If both are 0 or 1, it gives a 0. The second logic gate is an AND gate, which gives a 0 for everything except when both inputs are 1. If we wire these logic gates like this, we create a half adder, which gives 2 outputs, our sum and our carry. This allows us to add our binary number 1 bit at a time. A more complicated circuit is needed to perform the calculation in one step. Modern computers can perform millions of these calculations per second, and they're still getting faster. The co-founder of Intel, Gordon E. Moore, noticed a trend in 1965 that the density of transistors on integrated circuits doubles every 2 years. That trend has held until very recently, but it is starting to slow down. One of the reasons for this is the less well known of Moore's predictions, Moore's second law, or Rock's law, which states that the cost of manufacturing these devices will double every 4 years. Intel made an announcement last year that the rate of advancement was slowing for these reasons. It's getting more and more difficult for chip manufacturers to shrink their product while maintaining profit. Another problem that transistors are facing is quantum tunneling. As these transistors get smaller, so do the barriers between different sections. The barriers between each section of the transistor are getting so thin that electrons can pass right through them. With no definitive successor to the silicon transistor lined up, this incredible period of growth over the last 50 years could plateau in the near future. Some want to harness quantum mechanics to perform calculations faster than any transistor ever could. Others want to decentralize computing power and create the so-called Internet of Things. Intel have said themselves that they plan to shift their focus from increases in speed to decreases in power consumption. One thing is for sure, the computer industry will have to redefine itself in the near future. Thanks for watching. Thanks to your incredible response to their last sponsorship, the Great Courses Plus have sponsored me once again. So thank you to all my subscribers, Patreon supporters, and the Great Courses Plus for helping real engineering exist. If you enjoy my videos, you'll definitely like the Great Courses Plus. They have over 7,000 different lectures from world-renowned educators. They have a huge range of topics. If you'd like to learn more about electronics, they even have a course for that. Or you can learn about photography, chess, and cooking. These courses give you an in-depth knowledge of a variety of subjects, while allowing you to learn at your own pace, without tests or exams. You can get a free 1-month trial by going to thegreatcoursesplus.com/realengineering. If you'd like to see more content or support Real Engineering, the links for my Patreon, Instagram, Facebook, and Twitter accounts are below.